In this section, we're going to focus on several different things in section 1 of chapter 3. We're talking a little bit briefly about the history of the atom. There are 3 unique laws that we will address, and then also we're going to talk about the atomic theory, sort of the structure of an atom. Now, in terms of the history of an atom, there's a lot of different people that we can talk about here, and we'll go into more detail, and I will upload probably a video that kind of talks about the history maybe a little bit more as a story. But there's several people we're going to talk about. Democritus, we're also going to talk about Dalton, you also hear names Thomson, Millikan, and Rutherford. And we'll see more of them in section 2. Moving on. So the 3 laws that we're going to talk about. The very first one is called the law of conservation of mass. This will be one of the first labs that we actually will do probably the end of the week. Basically what the law of conservation of mass states is mass cannot be created or destroyed. So if we have a reaction involving 3 chemicals and the total mass is 20 grams, in the end there still has to be 20 grams somehow accounted for. So basically what we're saying is no matter what the chemical reaction is, we cannot gain or lose mass as that occurs. So just as a simple example here, we have 2 reactants, A and B, and together they total 10 grams. And a reaction occurs, and they make chemicals C and D. Well, again, there has to be a total of 10 grams. Now, how that is divided up, there could be, thousands of different combinations. 5 grams of each make 5 grams of each. 3 of A and 7 of B make 7 of C and 3 of D. Now, some people where they say, well, no, this doesn't always hold true. Well, usually when they're not paying attention, there's probably been a gas produced. And if a gas produced, it escapes. If it escapes, then the masses are thrown off. So you don't lose mass. It's just it may be in a form we do not see, recognize, or we're unable to capture. The lab we'll do is actually do just a simple lab of generating carbon dioxide, so sort of capturing a gas, and then again try to verify that the mass has not changed. The second law is called the law of definite proportions, or sometimes you'll see it called definite compositions. This is a really important one. What we're basically saying here is if you have a particular chemical, and whatever that chemical may be, there's only one possible ratio that the atoms can exist. Otherwise, it is a totally different chemical. What I mean by that is you can't have what we think of as water, H2O, in multiple proportions of hydrogens and oxygens. Okay? There's only one possible ratio, only one possible combination, and it's independent. It doesn't matter whether the amount of the chemical is or where the source is. So the 2 situations we have here, we've got water and we've got hydrogen peroxide. Chemically, water that we drink is 88% oxygen and 12% hydrogen by mass, and that's what it is. Any other percentages of oxygen and hydrogen in a chemical make it something other than water. If you notice here, peroxide is 94% oxygen and 6% hydrogen by mass. Again, if the percentages are anything else, then it's a completely different chemical. Right? There's definite proportions, one and only one way that a very specific chemical can exist. Multiple proportions. This is one we'll deal with more as we start doing calculations of chemicals and their formulas and things like that. So I'm going to do this very briefly, give you a couple examples, and it'll be something we just deal with throughout the year. So multiple proportions. Well, I mean, a couple things here. Number one, elements can combine together to make new chemicals, chemical compounds. But the only way they can combine is if they combine in whole number ratios. So, first example here, can carbon and oxygen bond together to make a new chemical? The answer is yes. And there's actually two very common ways that it can occur. The first way is in a 1-to-1 ratio, one carbon to one oxygen, we know as carbon monoxide. It can also form in a 1-to-2 ratio. Now, any other combinations of carbon and oxygen, number one, are not very common. And number two, if there are any other combinations, they have to be whole number combinations. We see here in hydrogen and oxygen, what are possible combinations here? Again, we're just limited to two that are naturally occurring and common. H2O, so a 2-to-1 ratio, and H2O2, a 2-to-2 ratio. We go to a third example now. We can look at one where there's more than just two. And this would be what we call hydrocarbons. We're going to talk about these later in the year, but they are carbon and hydrogen compounds. A common use or common source of these, fossil fuels. So, what are some common fossil fuels? CH4, C3H8, C4H10. We know them as methane, propane, and butane. So if we notice here, these are different ratios or proportions of carbons and hydrogens. They are whole number ratios, but they are unique whole number ratios. Are there more than this? Absolutely, for carbon and hydrogen. This is slightly different than law of definite composition or definite proportions, because they're just saying, well, if it's methane, methane can only be 1-to-4, and whatever that percentage would be. Multiple proportion says, oh, sure, they can combine, but if they combine, they must be whole number ratios. There cannot be any other variations to that. The last thing we're going to talk about here is Dalton's atomic theory. And John Dalton was a scientist who basically talked about the structure of an atom. He was one of the first ones to sort of theorize what is in an atom, what is it made up of, and some of its properties and characteristics. And for the most part, it held very true for a very, very long time. So as you can look those up and see them in the book and kind of write them down as you need to. Now, what I really want to talk about is which ones was he sort of off a little bit. And this is where we're going to talk about the difference between the modern atomic theory, which is what we currently understand, and Dalton's atomic theory. So what were the two differences? Well, in statement number 2 of Dalton's atomic theory, it said, elements are identical in nature. Basically, there are no variations. There's only one type of hydrogen and there's only one type of carbon. In reality, that when we talk about the same element, they can be different types that are not equal. Well, that's just what we call isotopes. And we'll talk more about isotopes specifically in section 2. The third thing, we talked about atoms cannot be created, destroyed, or subdivided. Well, kind of splitting hairs here a little bit. They can be subdivided into protons, electrons, neutrons. And we're also hearing about things like quarks and bosons, things like that. But you can't cut an atom and have half an atom. As soon as you cut an atom, you no longer have atoms, but you have pieces that make an atom. So technically, can atoms be subdivided? Well, they can be subdivided, but then it's no longer part of an atom. It's all these pieces that work together to make an atom. Again, I will have, with the notes here, a couple other links to some of the laws as well as Dalton's atomic theory, just to give you a little bit of supplemental information on those topics.